What are stars really doing up there? Stars aren't just pinpoints of light. They're giant nuclear furnaces creating the elements that make up our world. As NASA explains, except for hydrogen and some helium, all of the stuff we and the Earth around us are made of was generated in stars. Put another way, without stars we wouldn't even have the atoms, like carbon, oxygen, iron, needed for life. As the science writer Peter Tyson noted, every single atom in your body was created in a star billions of years ago. The light that built everything comes from stars that died long ago, knitting the very fabric of our bodies. A stellar nursery, the Orion Nebula is a vast cloud of gas and dust where new stars are born. Stars begin life in these cold, dark molecular clouds. Over time, gravity pulls clumps of hydrogen and dust together, causing a cloud to collapse. As it collapses, the core heats up. When the central temperature reaches on the order of 15 million degrees, nuclear fusion ignites. In other words, protons start fusing into helium, releasing a burst of energy. This ignition, often dramatized as a wondrous event, signals a newborn star lighting up. The Orion Nebula, star nursery, is one famous example. Hubble images show thousands of baby stars just coming to life within its glow. Once born, a star must balance gravity and fusion. Gravity relentlessly pulls the star's mass inward, while the heat and pressure from ongoing fusion push outward. This tug-of-war keeps the star stable for billions of years. In our sun's core, for example, about 500 million tons of hydrogen fuse into helium every second. That fusion liberates energy, ultimately as light and heat, which creates an outward pressure that exactly counters gravity's pull. It's like the star is breathing. Each inhale of gravitational squeeze is met by an exhale of energy from fusion. This steady energy output keeps the star shining and prevents collapse, essentially acting as the universe's long-lasting power plant. Stars are cosmic element factories. In their cores, fusion builds up heavier nuclei step by step. Small stars, like the Sun, fuse hydrogen into helium. More massive stars, those up to a few times the Sun's mass, compress their cores hot enough to burn helium into carbon and oxygen. In fact, our Sun will eventually fuse helium into carbon and oxygen when it swells into a red giant. Even larger stars, over approximately 8 solar masses, can fuse elements all the way up the periodic table, eventually producing iron in their cores. But there's a limit. Iron is the most tightly bound nucleus, and fusing iron no longer yields energy. To make any elements heavier than iron, things like copper, iodine, gold, or uranium, you need a supernova explosion. In that titanic blast, the star's debris is flung into space and new nuclear reactions occur. As NASA's Chandra X-ray Observatory notes, supernova remnants deliver elements such as iron, calcium, carbon, and more into the next generation of stars and planets. The very presence of life on Earth is due to the production of these essential elements from previous generations of stars. In other words, every atom of iron in your blood and carbon in your cells was born in the heart of a star or the fire of its explosion. What happens when a star finally exhausts its fuel? In high-mass stars, several times the Sun's mass, the end comes spectacularly. After expanding to a red supergiant, the iron core collapses under gravity. In less than a second, the core's temperature and pressure skyrocket to over 100 billion degrees, and the implosion rebounds in a supernova explosion. This is one of the most violent events in the universe. An outgoing shockwave rips through the star, forging even heavier elements and blasting them into space. The star briefly outshines its entire galaxy. For example, supernova 1987A in the Large Magellanic Cloud exploded over 30 years ago and became the closest supernova in centuries. It was observed by telescopes around the world, including Chandra, which still watches its glowing rings of debris. Each supernova effectively pollinates the galaxy with newly minted atoms. When a star dies, its remnant depends on its mass. White dwarf. Stars like our Sun, low to medium mass, swell into red giants and then shed their outer layers. What's left is a hot, dense core about half the Sun's mass, only approximately Earth-sized. This is a white dwarf. It no longer fuses fuel, but it is extremely dense, about 1 million times as dense as water. Neutron star. Massive stars end in supernova. If the core is between about 1.4 and approximately 3 solar masses, gravity crushes electrons into protons, forming a sphere of almost pure neutrons. This tiny object, about 10 kilometers across, is a neutron star. A teaspoon of its material would weigh 1 billion tons. Some neutron stars spin rapidly and beam radiation as pulsars. Black hole. If the collapsing core is even heavier, roughly over 3 solar masses, often from stars greater than or equal to 15 solar masses, nothing can stop the collapse. The core's gravity becomes so strong that not even light can escape. A black hole is born, an object whose gravity traps everything inside its event horizon. Do stars ever truly disappear? Not really, their remains live on. The gas and dust expelled by dying stars, in winds or supernova blasts, mix into the interstellar medium. Over time, gravity pulls this enriched gas into new molecular clouds. These clouds then collapse to form the next generation of stars and planets. In this way, star death seeds new beginnings. The iron in our blood, the oxygen we breathe, the silicon in our phones. Each atom has passed through generations of stars. We literally live in a cosmos of recycled stardust. Ultimately, every star and every living thing is connected by this cosmic cycle. Gas condenses into stars, stars forge elements and explode, and the debris forms new stars and worlds. One star's death becomes another's birth. In the words of Carl Sagan, echoed in modern astronomy, we are built of star stuff, the same material that stars create and return to the galaxy. That, more than anything, is what ties us to the stars above.